All right. Hello. Good evening, everyone. Welcome to week 9 of the JUPEB online tutorial class. And today we are going to be looking at differential calculus. So, without further ado, let's get right into it. So, what are we looking to achieve in today's class? Our lesson objectives are as follows. So, first of all, we're going to be looking at limits and continuity, understanding the foundational concepts of limits and continuity. Also, we're going to be looking at differentiation techniques, applying the various rules of differentiation to solve complex problems. We're also going to be looking at implicit and parametric equations. So by parametric equations, we're talking about equations where their variables are not easily isolated. And then we're also going to be looking at real-life applications to solving practical problems involving tangents, normals, extrema, and motion. So let's get right into it. So first, we're going to be looking at limits and continuity. So what do we mean when we say limit? So the limit of a function of x as x approaches a. So when we talk about limit of a function, if you think about it, all functions can be presented graphically on the graph, right? So we are basically saying what is the value of that function as it moves to a particular value, right? So more often than not, we tend to take our limit as a function tends towards infinity, right? But then generally, you can take a limit for a function at any given point. So the limit of a function as x approaches a is noted by this symbol. So for short, we describe a limit as lim, L-I-M, and then we put in the value x tends to a, where a can represent any number up till infinity. And the function f of x is equal to L, whatever our limit is. So this means that as f of x gets close to L, x approaches a without necessarily equaling a. So this concept is crucial for defining derivatives, right? So what do we mean when we talk about continuity? So we say that a function f of x is continuous at x equals to a if we have three conditions. F of a is defined, the limit x as x tends to f of x exists, and the limit f of x as x tends to a is equal to f of a. So you can have cases where you take a limit of a function at a particular value and it doesn't exist, right? So the function may not have a value, an answer at that particular value which you are taking a limit for. So in that case, we'll say that that function is discontinuous at that point, right? So the function does not have a value. There's a jump, and there are different kinds of discontinuity. Maybe a jump or a skip or whatever be the case, right? So there's a discontinuity at that point. But when we are working with derivatives, we want to have continuous functions, right? So we don't want to have any breaks or jumps or holes at the particular point we are taking our limit, because this doesn't help us. So, which is why we want to have a case where there is a continuity. So we have three conditions for testing this, and I've just listed them out. That f of a is defined. There is a limit of the function as x tends to a, and that limit is equal to f of a. So of course, we have an example here of calculating a limit. So basically what this is just plugging in the value which you have into the function and finding out if the limit exists. The limit of the function x squared minus 4 by x minus 2 as x tends to 2. So of course, x squared minus 4 is the difference of 2 squared. So x minus 2, x plus 2. X minus 2 cancels out x minus 2. And we have x plus 2, which is going to be 2 plus 2, which is 4. So of course, the limit of this function as x tends to 2 is 4. Now note, if we had just decided to plug in 2 here in the original function without expanding into the difference of 2 squares, we would have what? 0 as the denominator, and anything over 0 is what? Infinity, which would not be the correct answer. So of course, in limits, it's a rule of thumb that you should, as much as possible, break down the function to its simplest possible form before you now take the limit, right? So that's a rule of thumb which we should all have at the back of our mind. So differentiation from first principle. So the derivative of a function is defined as the limit of the average rate of change of the function as the interval approaches 0. So now that we've known what limits are, we now say that the limit of a function is the derivative of a function is taking the limit of that function as it approaches 0, right? So basically taking limit as the function tends to 0. That is what we mean by derivative. And of course, That is where we now get the concept of differentiation from its basic first principles, right? So, of course, this is a whole proof on how derivatives are arrived at from first principles. So now we get into actual differentiation, right? What are the rules that are involved? So we have three rules. We have chain rule, product rule, and quotient rule. So, of course, knowing these rules is important because when you're solving differentiation questions or finding derivatives, you would almost always result or revert to these rules because they are the most basic examples of functions that you can come across. Right. So the first one we're going to be looking at now is the chain rule. So it's used for composite functions, a function within a function. So it's also called function within a function. So if y is a function of u and u is a function of x, then we can simply apply the chain rule and say that dy dx is equal to dy du times du dx, right? So this rule is essential when dealing with powers of functions or trigonometric functions of an expression. So for example, if you have two functions together, maybe you have a trig function and you have an algebraic function. So for example, you have something like sine 3x squared. Now, normally you would be able to differentiate sine x. Of course, if you have your cheat sheet for differentiation, you should know that the differentiation of sine x is going to be 0 cos x. But if you have something like sine 3x squared, that is less straightforward, right? So let's just confirm that. So this is a sample cheat sheet for differentiation. So it's something you should also have um with you, easily accessible, because there are some common derivatives that always come up that you should be able to know. So um so if you have something like derivative of sine x is cos x, right? That's straightforward. We all know that. However, if you have something like sine 3x squared, you can't simply say that is cos 3x squared. No, because you have a function, an algebraic function within the trigonometric function. So that is where you will now apply chain rule, where you would now say, let you introduce a second function, right? So we have y and x. Introduce a third function u and say let u equal to 3x squared, right? And so y is now what? Sine u. So now your dy dx would now be dy du times du dx. And doing that, you would now be able to find the derivative of sine 3x squared without having by them applying chain rule, right? So that's function within a function. It can also apply to any other combination of function within a function. And you can do it multiple times depending on the kind of example you're given, right? So next we're going to be looking at now is product rule. So applying product rule, as the name implies, is when we have products, right? It's when you have two functions multiplying each other. So if u and v are both functions of x, then the derivative of their product is u dv dx plus v du dx. So for example, to differentiate y equal to s squared plus 1 times s squared minus s cubed minus x, what you will simply do is, you see we have two functions here multiplying each other, right? So what you would simply do would be to do to assign a name to each one of these functions. So you say, let this be u and let this be v, right? So you will say u times dv dx, which is the differentiation of this one, plus v times du dx, which is the differentiation of the other one. Okay, so now this is applying the product rule, right? Because you can't simply apply a chain rule here, because this is not a function within a function. This is a function multiplying another function. So this is the way to apply the product rule to be able to now find the derivative of the general function y or f of x. Then we also have the quotient rule. Quotient rule is used, of course, as the name implies, when we have a division. So while this one is useful when we have a multiplication, which one is useful when we have two functions as a division. And of course, we have the same principle. One takes u and one takes the v. But now in this case, the formula is different. So the formula for the derivative is v du dx minus u dv dx all over v squared. Now, a very important point to note is that u and v are both functions of x, and v is not equal to 0, of course, because u is normally the numerator and v is the denominator, and we can't have the denominator being 0, right? Of course, that does not give us that gives us an answer that tends to infinity. So of course, v du dx minus u dv dx all over v squared. So this is used when you have divisions, functions dividing each other. and you apply the quotient rule to be able to find the derivative of the function. So the next thing we're going to be looking at now is implicit differentiation. Now, implicit differentiation is a technique used to find the derivative of a dependent variable with respect to an independent variable when the relationship between them is not given in an explicit form. That is y is not isolated. Yeah, that's a lot of grammar. That's a lot of English. Let's look at an example, right? So, for example, now we have this equation x squared plus y squared equals 25. Now, under normal circumstances, the kind of equations we have been used to are the ones where we have y is equal to something, 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 something. And all of that something, something, something is all in terms of x, right? And so it would be easy for you to simply just treat all of that as a function of x and divide straight up, right? However, we now see that we are trying to find the derivative of a dependent variable with respect to an independent variable when the relationship is not in an explicit form. Now, what do you mean by explicit form? Y is not isolated. Now we see that y is within the function itself, right? So one way to do this would be to decide to make y separate a formula here and now treat it as a normal explicit differentiation. However, that would yield to more complex equations, right? So one way of dealing with this is to now do what we call implicit differentiation, where we differentiate with respect to x, right? Because y is our dependent variable, and we want to find the y dx. So we differentiate everything with respect to x. So we differentiate x squared first, right? We differentiate x squared versus x, that yields what? 2x. That's a normal differentiation. Now, if we differentiate y squared with respect to x, you get 2y. But now, since y is your dependent variable, you now have to attach what? Dy dx to it, right? Because you're differentiating your dependent variable, and your variable depends on x. So you have to have a dx because it's changing with respect to x, right? So we differentiate that and add the dy dx, and then we differentiate the constant, and then differentiating the constant means that it goes to 0, right? Now, what do? We simply make the y dx so to the formula. We solve for the y dx, basically. And in doing that, we see that the y dx is equal to minus x over y. So this technique is essential for equations where isolating y is difficult or impossible, just like I said. We've just looked at what implicit differentiation entails and tried to explain why this is preferable than deciding to make y the root of the formula. So you would have something like square root of 25 minus x squared. So that is a more complex application of a function within a function, while it is much easier for you to simply apply implicit differentiation here and arrive at your answer of the y dx. Right. So moving on, the next thing we're going to be looking at now is parametric differentiation. Now, parametric differentiation is used where both x and y are expressed in terms of a third variable, often t. Now, this allows us to find the y dx without having to eliminate the parameter first, which can often be a complex or impossible task. What do we mean? So, for example, we are given x and y are given in terms of a function t. Now, we can find the dy dx without having to remove that variable t by the use of a simple formula. So if x is equal to f of t and y is equal to g of t, we can find the y dx by simply doing the y dt divided by the x dt, provided that the x dt is not equal to 0, of course, because we have a division, so our denominator cannot be 0. So we have a very simple example here which illustrates this. So we are given x is equal to t squared and y is equal to t cubed. So of course, what do we need? We need the y dt and we need the x dt. So we find the y dt. So now we differentiate y with respect to t, and that's going to give us 3t squared. Next, we differentiate x with respect to t, and that's going to give us 2t. And now the formula says we divide. So we have 3t squared over 2t, and that should give us 3t over 2. So this is particularly useful in physics and maths and engineering because more often than not, our equations are always given in terms of a third parameter, which is usually time. So we have to be able to link our variables without having to go through the complex process of eliminating the third parameter, which we do not need. The next thing we're going to be looking at is applications of derivation. So very common application which you all will be exposed to is using it to solve tangents and normals. So they are direct applications because what is differentiation actually in the real sense? Differentiation is what? Trying to determine rate of change. So when we have a function they call, when we are differentiating, we are trying to find how is y changing with respect to x. So for every x I move, how is the y part of the graph changing? For every, when it comes to equations of motion, for every step I take, for every time, every second that counts, how is my distance moving? If which is why, of course, you see that the case is when we differentiate a constant, we get zero. Now think about it, because nothing is moving. So if you think about it in terms of motion, if you have a constant speed, right, your speed is not changing. For every time that moves, for every time t that counts, your speed does not change. There is no acceleration. So if you want to find a rate of change, there is no rate of change. And so if you have a constant term, if you differentiate it, you're going to get zero, which makes sense because there is no change, there is no variable, nothing is moving. But then if you are accelerating, for every time t that is moving, for every second that is adding, your velocity or speed is increasing, and so there is a rate of change. So what does differentiation help us? Differentiation helps us to determine, okay, for every time t, for every second that counts, how is this car's speed changing with respect to that? And of course, this rate can be increasing or decreasing. We also see this concept when it comes to flow. If I turn on this tap, how is the rate of the water with respect to time? Is it flowing at so and so speed or rate? So these things are important in real life applications, which is why differentiation and knowledge of it is important as well. Right. So we're going to be looking at applications in tangents and normals and equations of a line. So of course, a tangent is defined here as a straight line that touches a curve at a single point without crossing it at that point. Its slope at that specific point is given by the derivative of the function f prime of x. So this f prime of x simply means differentiating the function of x evaluated at the point of tangency. The normal is a straight line that is perpendicular to the tangent line at the point of tangency of the curve. So at the point where the tangent line passes the curve, you draw a line perpendicular to it at that point, and that is called the normal line. Now the slope of the tangent is m, and the slope of the normal is minus 1 over m. Next, we have another application which is in the equation of a line. So both the tangent and normal lines can be found using the point slope form of a linear equation where y minus y1 is equal to mx minus x1, where x1, y1 is the point of tangency and m is the respective slope. So, of course, this is used in curve analysis, optimization, and other physical applications where we are dealing with motion. The other application is to maxima and minima. So, of course, we have cases where we have a curve or a graph or something that is an illustration of an actual real world example, and we want to find the maximum and the minimum points. And the maximum and minimum points are usually very important because those determine our skew points, the points where the extremes. And it's always important to find the extreme because we want to know how fast did this car get to, how slow was this car, how was the slowest time it took the water to fill the bucket, things like that. So of course, knowing our maximum and minimum points are always important for any given rate of change of function we are dealing with. So differentiation also plays a very important role in finding this, right? Because we are also dealing with change. So the first derivative test to find the potential maximum minima, first calculate the first derivative and set it to 0 to find the critical point. It's at the point where the function slope is 0. Now, once you find the critical point, you now have to know. So what do we mean by critical points? Critical points are the points where the curve changes direction, right? So imagine a curve is sloping downwards and then it wants that to going upwards. It first of all has to come to a kind of plateau or a valley in this case, and then start going upwards. Now at that point where the curve is turning, for a little while, the change is 0 because the curve has to first of all come to a pause and then turn upwards. So what is your first derivative? Your first derivative is to find those critical points. Do those points in this graph exist where the function slope is 0? And of course you find that by taking your derivative because that's how you calculate slope. Now, having found those critical points, you now have to determine, is this a maximum or a minimum? Is this an upward slope or a downward slope, right? And that is now where you do your second derivative test. So when you identify the critical point, second derivative test now helps you to determine if the point is a maximum or a minimum. So if the second derivative, that's f prime prime of x, is greater than 0, then the function has a local minimum, right? So if it's less than 0, the function has a local maximum, right? So an example, a quick example given here is the function this. So first of all, you differentiate once, and you have what? 2x minus 4, and then this goes to 0. So now, to find the critical point, you set this first derivative to 0, right? So setting it equals to 0 gives you that x equal to 2 is a critical point, right? Now, you now differentiate the second time, right? Now, differentiate the second time, you see that you have 2 as your second derivative. Now, since 2 is greater than 0, it means that it's a local minimum at that point. Remember our condition. If you f prime prime of x equals to 0, then it's a local minimum, right? Now, you would have had a case where if you do the second derivative, you would still have a function of x left. What you would have then done was now substitute x that you've got here as a critical point into it. And then if your answer was greater than 0, you'd have a local minimum. If your answer was less than 0, you'd have a local maximum. Fantastic. So the next application we're going to be looking at now is applications in motion. Applications in motion, right? So of course, this is very useful. Derivatives is very useful in motion because, like I said, we're dealing with rate of change, and motion is basically things that are happening with respect to time, things that are changing with respect to time. So we have a relationship between displacement. So we're working with the vector quantities now. So displacement, velocity, and acceleration instead of distance and speed, right? So so for displacement, the function describes the position of an object at a given time t. This displacement is always the starting point of all motion analysis. Now, velocity is the rate of change of displacement with respect to time. That's English. In math, what do we mean? Velocity is the s, the t. So s is displacement, t is time. So velocity is how is s changing with respect to t. And that's why we have the s, the t, right? Now, acceleration is rate of change of velocity with respect to time. Now, that's English. In math, acceleration is dv dt, because for you to accelerate, your velocity must be changing, either increasing acceleration or decreasing deceleration with respect to time. So this follows that the first derivative of velocity is acceleration. The first derivative of displacement is velocity. The second derivative of displacement is acceleration, because if you differentiate displacement, you get the velocity. If you differentiate the velocity, you get the acceleration. So of course, all these points of motion, all these relationships are established between our various terms in motion. So quick example is given here. If you have the displacement of an object given by this, so s of t, s is displacement, and t is the independent variable time. So this is all given in terms of t. What will be your velocity function? We simply to differentiate s, right, with respect to t. And that will now be 3t squared minus 12t plus 9. Now, if you were to go further and differentiate to get the acceleration, you would now do what? dv dt, which would be d squared s dt squared, which is simply the second derivative of displacement, or the first derivative of velocity. This would give you acceleration. So you would now have 60 minus 12. Now, these are the equations of motion for all the different parameters for this object. If you are not asked to find, okay, what is the acceleration of this car at t equal to a certain point, maybe t equal to 5 seconds, what you would simply do would be to substitute t into the function, and you'll be able to arrive at your answer. And now you can do this for the different points in time t and see at each point what was your acceleration, or what was your velocity, what was your distance. And that gives you an idea, of course, if you want to model, to see how the motion was changing, how the patterns of motion at each and every point in time. So I mean, this gives you wonderful insight into equations of motion. So these are like real world example, real life applications of these things. It's not just theory and putting things on paper. We actually use these things in real world examples to solve problems. So yeah, we have a few practice questions here. So if you're watching this, you can just take out the time to try these. So this is a differentiation here, which you're going to do with chain rule. So we have a function, or algebraic function, we need a trigonometric function, y equal to sine x squared. You're also required to find the tangent to this function at x equal 1. If you don't know how to do that, it's covered in the video. You can just simply go back and look at the formula given. Solve x squared plus y squared equal to 10. Find the y dx. And given s of t equal to t squared minus 2t, find v of t and a of t. Fantastic. So with that, we have come to the end of today's session. Quick summary of what we covered. We looked at limits and continuity. We applied differentiation techniques. First principles, chain, product, quotient rule, differentiated implicit and parametric functions. And we looked at a lot of applications and practical problems involving tangents, normals, minimum, maximum, and equations of motion. Thank you very much for making out the time joining me on this episode of JUPEB Math class for 9. Hope you've been able to gain a lot of value from everything that we looked at today, and hopefully it will your time. Thank you very much, and buenas noches.